In astrophysics, accretion is the accumulation of cosmic dust particles into a massive object by gravitationally attracting more matter, typically gaseous matter in an accretion disk. This attracted matter accelerates the growth of the particles into boulder-sized planetesimals. The more massive planetesimals accrete some smaller ones, while others shatter in collisions. Accretion disks are common around smaller stars or stellar remnants in a close binary or black holes in the centers of spiral galaxies. Some dynamics in the disk are necessary to allow orbiting gas to lose angular momentum and fall onto the central massive object. Occasionally, this can result in stellar surface fusion. Overview: the proposed idea in the 19th century that Earth and the other terrestrial planets were formed from meteoritic material, was developed in a quantitative way in 1969 by Viktor Safronov, who calculated in details the different stages of terrestrial planet formation. Since then, the theory has been further developed using intensive numerical simulations to study planetesimal accumulation. In the formation of terrestrial planets or planetary cores, several stages can be considered. First, when gas and dust grains collide, they agglomerate by microphysical processes like van der Waals forces, electromagnetic forces, forming micrometer-sized particles. During this stage, accumulation mechanisms are largely non-gravitational in nature. Accumulation in the centimeter per meter range is not well understood, and no convincing explanation is offered into why such particles would accumulate rather than simply rebound, but it is hypothesized that when slow-moving grains collide, the very low gravity of the mass impedes their escape. Grains stick together to form mountain-sized bodies called planetesimals. Collisions and gravitational interactions between planetesimals combine to produce moon-sized planetary embryos in roughly 0.1 million years. Finally, the planetary embryos collide to form the planets in 100 million years. The planetesimals are massive enough that mutual gravitational interactions are taken into account in computing their evolution. Growth is aided by orbital decay of smaller bodies due to gas drag, which prevents them from being stranded between orbits of the embryos. Further collisions and accumulation led to terrestrial planets or the core of giant planets. However, the physics of planetesimal formation are not understood, or how the planets came to have their present chemical compositions. In particular, it is still not clear how these objects grow to become 0.1 kilometer-sized planetesimals. This problem is known as the meter-size barrier. The formation of terrestrial planets differs from that of giant gas planets or Jovian planets. The particles that made up the terrestrial planets were made from metal and rock that condensed in the inner solar system. However, the Jovian planets began as large, ice planetesimals, which then captured hydrogen and helium gas from the solar nebula. The planetesimals which form the two types of planets differ due to the frost line. See also, Bondi accretion, nebula hypothesis, nova, planetary nebula, protoplanetary disk. References